Okay, according to my watch, we are at 11 a.m. Pacific time, which means that we are going to get started. Hi, everybody, and welcome to Quantum Analytics webinar. I am Lauren Armstrong, Marketing Director for Quantum Analytics, and I will be your moderator for today's event. Today, we're going to show you how to adapt GC-based standards for sampling and analysis of PFAS in air. We are very excited to be joined by Hannah Calder, Environmental Air Market Development Manager for Marks International. Hannah has a comprehensive knowledge on the use of thermal desorption as an analytical tool for air analysis and is involved with the development of international analytical standards for ambient and indoor air monitoring through ASTM Committee D22. During today's session, Hannah will be sharing with us how current VOC monitoring standards can be applied to PFAS monitoring in air. Before I hand the mic over to Hannah, I wanted to share a quick note about quantum analytics. We are a value added distributor of analytical instrumentation. We are a one stop shop for the busy lab manager, offering everything from rentals to financing and leasing on new or refurbished instruments. And we also offer consulting services for new lab startups. And we also specialize in solutions that enhance the Agilent GC portfolio, GC and LC portfolio. And that includes systems like the Frontier pyrolysis system and the Marks thermal desorption system that you're going to learn about today. We are a proud distribution partner for Marks International, which means you can purchase, rent, or finance the Marks solutions you learn about today directly through Quantum Analytics. All right, as a registered guest, you're going to receive a link to this recorded webinar in your email as soon as it becomes available. We've reserved about an hour for this webinar, which includes Q&A. So at any time during the webinar, if you have a question for Hannah, go ahead and type it into the question module that you see on the right side of the screen. We're going to keep a roster of these questions and pose them to Hannah at the end of the webinar. All right, that ends our introduction. So without further delay, I present to you Hannah Keller. Hannah, take it away.
Thanks so much, Lauren. Hi, everyone, and thank you for tuning in today. Today, I'm going to be talking to you about how we can adapt some GC-based standards, which are already used for air monitoring, for the tricky problem of PFAS. But before I do that, I wanted to give you a quick introduction to Marks International. So, Marks have been manufacturing instrumentation for air monitoring for over 25 years. We have a wide range of products for sampling and analysis of trace volatile and semi-volatile organic compounds, and this includes our range of pre-concentration instruments, sampling accessories, a wide selection of sorbent tubes, and of course instrument spares to make sure that you've got everything you need for thermal desorption. We have worldwide partners, including Quantum Analytics in the USA, and we personally have centers of excellence in Cardiff in the UK, Frankfurt in Germany, Sacramento in the US, Toronto in Canada, and Shanghai and Beijing in China. As part of the presentation today, we'll be going into a little bit of background about PFAS in air, the lesser talked about matrix for PFAS analysis, and a quick catch up on thermal desorption for anyone who's not familiar with it already. Then we'll move on to the standards that we can adapt for PFAS monitoring and look at some different sets of PFAS compound that are emerging as important to monitor in air, including what we're going to term classical PFAS and products of incomplete destruction, or PIDs, as they're also called. So let's start with why PFAS in air is going to become important for monitoring. Now, put fairly simply, air is a way that PFAS can be spread very quickly over a wide area. For years now, there have been plenty of presentations at analytical conferences talking about how PFAS contamination investigators were surprised to find PFAS upstream of manufacturing sites or in locations where no known AFFF had been used before, and absolutely puzzled as to how it got there. And in the majority of cases, if there hadn't been some sort of spill, it got there because it was carried there by the air and then deposited into the water and soil. A study by the US EPA in 2021 modeled how much PFAS, if it was emitted from a site, would be deposited within 150 kilometers of that site. So to put this into sort of context, you've got a map of the UK on the right-hand side of the screen here. That little dot in the middle is where our factory site is in South Wales, and the black ring around it is 150 kilometers. What the US EPA found was that if Marks were very unlucky and we had a PFAS manufacturer right next door to us, only 5% of the emissions that came from that PFAS manufacturer that were released into the air would be deposited within that black circle. So 95% of all of the emissions from a PFAS source will travel further afield. And that means it's got the potential to spread it over an entire continent. So it's going to be a really important issue and one that governments are gearing up to try and do something about. Regulations and methods for monitoring PFAS in air are beginning to be released. And they're beginning to be released for multiple different sources and environments. So in the EU, there's beginning to be a focus on emissions from products. So what are workers being exposed to? What are consumers being exposed to from emissions? We're also thinking of landfill gas, or what is happening when PFAS themselves are being manufactured, are being incorporated into products as well in terms of manufacturing emissions. And then there's the issue of how you dispose of your PFAS. If we're destroying them, are we really getting rid of them? Or are we just converting them into something else, which is then kicking the can down the road and is creating a different problem? But as I'm sure many of you on this call today know, PFAS, it's an easy term, but it actually covers a whole load of different compounds with different properties, from the polymer PFAS to your monomer PFAS. So many different chemistries involved within that as well, and so many different volatilities. And the majority of PFAS methods that have been released so far have been on LC, but LC isn't going to be able to cover everything. It's doing an excellent job at looking at the perfluorinated sulfonic acids, the perfluorinated carboxylic acids down to C4, ionic species, and of course LC is great for semi-volatile compounds. So any larger PFAS species, LC is doing a good job. But where we're now beginning to see gaps in what LC can monitor, or monitor to the level that's required, is for things like the volatile species and neutral species. But this is where GC, with a pre-constant technique in front, then becomes interesting. So GC, excellent for volatile species. It's also proven to be more sensitive in early testing for a lot of the neutral PFAS species, such as the fluorotellumer alcohols, for example. It also can do perfluorinated carboxylic acids with some caveats, but it then struggles with the sulfonic acids and many of the ionic species. So there's balance here. We will absolutely have to continue to use LC for some monitoring in air, but there's also a massive benefit to using GC for that monitoring. And in terms of pre-concentration, There are a few different methodologies we could use, but all of them will involve sorbents. Thermal desorption as a pre-concentration technique using sorbents is one of the highest sensitivity techniques you can use, because at no point do you need to dilute that sample. There's no need to elute with solvent. You don't need to add any extra air or anything like that to repressurize the sample. It's simply a case of taking your sample volume onto the adsorbents within that sorbent tube. This could be multiple sorbents, 2 to 3, depending on what you're trying to collect. That tube can be sampled in the field. It's then taken back to the lab, desorbed in your carrier gas for your GC, and then thermal desorption will typically employ a second stage of focusing as well. And this happens with the focusing trap inside the system. And again, this can be packed with multiple sorbents, so you can look at a really wide range of compounds without having to do any complicated method development. Once you've got all of your compounds onto that focusing trap, it's then injected into the GC in a really narrow band of gas, so 100 to 200 microliters. And then that's what hits the front of your GC column and is then chromatographically separated, ready for detection. Now, for PFAS, we're looking at low picogram per meter cubed monitoring in air in certain situations. So that really will require analysts, researchers, and people involved in environmental forensics to take hundreds of liters of sample. But with the fact that you don't have to dilute with thermal desorption, you can take less sample, which is going to take less time, and you're going to get your results quicker. Okay, so PFAS in air with thermal desorption, we can measure a whole range of different species, as we said earlier. But I'm going to split these into two areas, essentially. So I'm going to talk about what we can do for your sort of classical PFAS. So when I'm saying classical PFAS, it's the compounds that really we're already looking at in water is what we're talking about here. Well, the ones that are GC amenable anyway. So you've got your perfluorocarboxylic acids, your fluorotellumer alcohols, your FOSAs, your FOs, and more in between. But when it comes to the second class of compounds, the products of incomplete destruction, what you see is that you get a big shift in volatility. So if we take something like GenX, which is a massive, replacement compound, really widely used, we look at the original boiling point for GenX, and if we're disposing of GenX, one of the methods is to thermally degrade it, and that degradation will result in a decarboxylation. When we get that reaction happening, we've then got the fluoroether E1 produced. And this has a significantly different boiling point. We're going from something that's, on the range of being semi-volatile in air to something that's now really volatile. And when we change that chemistry and when we change that compound, it means we need to start thinking about things in a slightly different way in terms of our sample collection. And in terms of products of incomplete destruction, the fluoroether is just one example of a degradation that we know happens when compounds like GenX are disposed of. But in reality, if you're not disposing of your PFAS completely, one of the most common compounds that you will actually see generated and then released into the atmosphere, if it is thermal degradation, is this Freon 14 or CF4. And this is an ultra volatile compound, one of the most volatile compounds that you can capture using canisters and then analyze using thermal desorption GCMS. So this is going to require a slightly different way of thinking. And that means we need to think about different standard methods that we can adapt then to address this problem. So for our classical PFAS, we might be looking for them in ambient air, indoor air, maybe vapor intrusion for indoor air, and then of course from materials, because they could be coming from materials that we have in our homes, we have in our offices, or that we are using in our jobs. And for those classical PFAS, we can use sorbent tubes because they are in a volatility range where we're going to be quite comfortable sampling them onto sorbents, and because they might be present at levels where we need to take quite a large sample size to get the sensitivity we need in the GC. But for the products of incomplete destruction, because they're so much more volatile, we're now looking at canisters for that sample collection. And that completely changes where we start developing our methods from. So for the classical PFAS, in ambient air and indoor air, we can begin with a method TO17, ISO 16017 maybe as well, or even ISO 16000 Part 6. All of these are well established, well understood thermal desorption methods with an separation by GC and detection by MS. But for the materials then, we need to think about a slightly different sampling method, but we'll still be using sorbent tubes. So we can turn to some of the ASTM methods for materials, like ASTM D7706 Part 11, which uses microchambers to take that sample, transfer it to a sorbent tube, and then you analyze with ISO 16000 Part 6, or one of the ASTM methods as well. Now, for our canister method for PFAS destruction, we're then thinking about TO15 and TO15A. As TO15A is the most recent and it deals with compounds at a much lower detection limit than TO15, this makes it the most sensible choice to begin with here. So let's begin looking at our adapted TO17 method for sorbent tube analysis. So whenever we're developing a method, we always start with what we want to actually monitor. What are our target compounds? Now, in this case, we've taken every compound that we could find in the Wellington catalogue that we thought would be amenable to GC. So that's your PFCAs, so your perfluorocarboxylic acids, to give it its full name, your fluorotelomere acids as well, so FTCAs, your fluorotelomere alcohols, FTOHs, your fluorotelomere acrylates, FTACs, your perfluorooctane sulfonamides, your FOSs, and then your perfluorooctane sulfonamide aminoethanols, or your FOs. I always regret saying all of those names out loud whenever I give this presentation. Always get stuck on the FOs. But this is, this is 19 different compounds. It's not the 50 to 60 that we're doing in water yet, but it's a good starting point. And it covers those compounds like the fluorotelomere alcohols, which the LC methods really can't do as well at the moment. So you've got our target compounds. Next, we're looking at, all right, how are we going to capture this? And this is where we begin to deviate from your traditional TO17 sorbents. Our PFAS are not as volatile as some of the compounds we're looking at in TO17. So what we can do is we can create a sorbent tube that's more suited to the volatility ranges that we're seeing within that group. Okay, so once we've come up with the sorbent, what we then need to do is test it for suitability. Now, our ideal detection limit is in the range of 1 to 50 picograms. Okay, so that's quite low. And the way that we test whether the sorbent tube is going to be suitable for taking a volume that will allow us to reach those detection limits, knowing what we do about the sensitivity of the MS that we're going to use, is we spike our target analytes onto one sorbent tube. We connect a second tube to the back of it, which we call a breakthrough tube, and then we challenge that tube with a high volume. And in this case, we've challenged it with 500 litres to see if we can still retain those target species after passing 500 litres through that tube. And when we're looking at breakthrough, what we're really looking at is not that we don't see anything on that backup tube, but that we don't pass that 5% breakthrough limit threshold. And what we've seen with the testing that we've done is that for all of the compounds tested, we were able to put 500 litres of air through this tube and not have breakthrough of any compounds, which gives some real confidence that when we go into the field, if we do need to take a very high volume to try and get down to, the levels that we're expecting to see in the air, or levels that might be significant within future legislation, we're going to be able to do it with this sorbent tube. Our breakthrough testing, we tested with 5 replicates, and we've now determined that our PFAS tubes are optimal for this type of sampling. So that's a great start. So next, when we're adapting our TO17 method, we've changed our tubes. So what we're also going to do is we're going to have a look at that trap recipe as well. Air toxics, again, really volatile. We probably don't need as strong sorbents in that focusing trap as we would for a full air toxic suite. So what we've done is we've created a PFAS focusing trap, which then matches more closely the sorbents within that PFAS sorbent tube. What this means is, because we've got similar sorbent strengths within our tube and our trap, we can do a bit more in terms of water management now. And that's really important because if we're going to be taking hundreds of litres of, say, for example, ambient air, that ambient air could be incredibly humid. And we're going to be sampling a lot of water at the same time. Being able to do more water management in the form of dry purging and also something unique to Marks, an elevated trap purge to remove water twice during the analytical process in an automated way, we've got the best chance of getting rid of any interference that water might have for the analysis. And then to ensure that we've got a stable method and we can spot if anything goes wrong, we've got an automated addition of an internal standard as well, which in this case was toluene D8. So that's what we're doing on the sample introduction with the TD100XR. And then for the analysis, we're using GC triple quad here. And that's because we want to make use of that MRM mode for looking for our targets. And I'll show you why in a few slides' time. We can also look at non-targets with the triple quad as well. So we've got a bit of flexibility there if we did want to do an untargeted method too. But in terms of the chromatography, what we found was really important when we started setting this up was actually the column that we were using. So we've tested 3 or 4 different column phases for PFAS, and we found that a 200 ms column was the best possible column for getting separation of the acids. Because acids interact slightly unpredictably with GC column phases. And I've heard a few theories as to why from people who are better at chromatography than myself. But the result is that you get, with the 200 ms column, you get to a point where you can separate the PFBA and the PFPEA, so the butyl and the pentyl acids. We've got good resolution for everything else, lovely sharp peak shapes from that really quick injection from the TD, and these compounds were still stable on this column after over 500 injections. So a really promising start to a robust and repeatable analysis. And anyone who's done PFAS analysis will know that there's always that question hanging in the background, PFAS background. Elsie had big problems at the beginning with PFAS background within the systems. You now have to buy a PFAS kit to upgrade your HPLCs with if you're doing this analysis. And when we were developing our methods, we wanted to be completely sure that we weren't getting PFAS background from the instrument. A lot of, well, pretty much every single GC will have some sort of fluoropolymer included within the flow path somewhere, whether it be O-rings, whether it be some ferrules have fluoropolymers in them, whether it be use of PTFE within the systems as well. And what we can't do with PFAS, and what we've seen from Elsie, is get rid of everything, because you still need parts in your system that are going to work. But what you can do is make sure that you understand where your background is coming from, and you can then adapt what you're doing to set up protocols to do other stuff. Thankfully, what we're seeing from the TD100 is that the instrument itself doesn't give any PFAS background. Absolute win. Really pleased. And we've done that here. Well, the example you can see here is where we've taken the SIM ion of 131, and we've also looked at the total ion chromatogram as well to see if there's any other background. And this was a TD100 which came directly off the factory floor after it had been through its final testing procedure. So it's not been conditioned, it's not been run in. This was the first test that was done on it, and we've got no background. Brilliant. So yeah, real confidence that the instruments themselves are more than capable of handling any challenges and aren't going to create questions for that analysis. And then we come to the method performance. Now, I'm not going to show you the linearity and repeatability. They were well within what TO17 requires as our base method. But here we can see some of the excellent method detection limits that we've gone. So to get these method detection limits, what we've done is we've followed the US EPA method, which is the most stringent. You run 7 spiked sorbent tubes at a challenge level. Typically for us, this was 10 picograms on tube, and then you run 7 blanks as well. Any compounds where your blanks are higher than your spikes level, you take the background rather than the spike for your MDR. Really sensible way of doing with it, and really helps to deal with the fact that PFAS are everywhere. So yeah, a really robust way of looking at it, and that's what we've done here. And you can see that, I mean, for the FOCs, we've got an average method detection limit of 1 picogram, which is absolutely outstanding. Ranging then through to the fluorotellium alcohols at 8 picograms, and the highest detection limit we had was for the fluorotellium carboxylic acids at 48 picograms. This is actually just because the response in the MS for the fluorotellium carboxylic acid isn't as high as some of the other compounds, which you can actually see if we go back to our chromatogram here. FOEA and FHEA got a really low response, and that's the only reason we're getting a much a much higher method detection limit there. But it's also well within our 1 to 50 picograms. So we're right on the money with what we were aiming to do when setting up this method. And if we then think about the method detection limits that's possible when we're taking a 500 litre sample, we're getting in the range of 2 to sort of 100 picogram per meter cubed that we'd be able to analyze if it was actually coming from the environment. So I said earlier on that we'd be showing why we chose a triple quad for this particular analysis. And when you're starting to sample 300 litres with a technique that is as sensitive as thermal resorption, you begin to get a lot of response. Typically for TO17, I mean, you're taking a litre of sample. So depending on the compounds you're looking at, etc., etc. But, 300 litres is 300 times more. So we've got a really big jump in the amount of sample we're introducing into the system. And you can see that in the chromatogram here. We've got an abundance of 10 to the 9 for this 300 litre ambient air sample. And this air sample was taken from a light industrial location, so not as clean as rural background, but also not particularly polluted either. When we then looked at the PFAS in that sample, you can see that our abundance here is 10 to the 5. So 4 times lower. Well, no, you know what I mean. Over 1,000 times lower than in the previous sample. And yeah, that's a massive difference. I mean, the chances of us finding some of the fluorotelem alcohols, which are at really low levels here, in a scan, even if we're using SIM on a single quad, it's really going to be pushed to find these compounds. And that's the reason that certainly for tube analysis, all of the methods that we're aware of, which are in writing, either with the US EPA or through ASTM, are utilizing triple quad for the detector. But that doesn't mean there aren't other options. Certainly in research, we're still seeing a lot of high resolution MS being used. But for, if we're talking about a routine analysis, it's high resolution MS is never going to be the solution. For that, you're going to want a workhorse like a triple quad, really. So we'll just have a look at a quick case study. We've had a really good collaboration with NILU, who are the Norwegian environmental research organization. And they were interested in looking at how PFAS in air might be affecting animals. So they took samples from a small organic farm in Norway. It's got a barn, a vegetable patch, and some livestock, which includes pigs and chickens. And where they wanted to sample was at the pig pen and the chicken coop. The sampling points you can see indicated on this picture with a yellow circle with a cross in it. And again, some more pictures here showing you where the samples were taken from. And you'll notice in the aerial view that these two locations, they're pretty close to one another. Okay, so we're expecting roughly the same kind of concentrations, the same kind of profiles. And broadly, you can see we've got that when we compare the TIC for the pig pen and the chicken coop. You see some lovely acids in the chromatogram there, lots of different peaks. So then let's look at the MRM and see if we can find any PFAS in it. And what we were really surprised to see, and certainly what NILU were really surprised to see, was firstly this really huge peak for the tetradecanoic acid. It's over 2 nanograms. It's absolutely huge. And what we saw was that it's much higher concentration in the pig pen than it is in the chicken coop. So, which really indicates that there is a point source in the pig pen, which is then generating these compounds. Our collaborator, Vladimir Nikiforov, was doing some research and found that it can be emitted from certain lights that are used in chicken coops. But that didn't necessarily make sense of why it was in the pig pen rather than the chicken coop. So it's still a bit of a mystery, and they're going to do some more sampling to try and figure that out. But it was really interesting to see that we got a range of acids, more commonly the more volatile ones, which potentially makes sense. There's certainly a lot of discussion about whether you should really be seeing the acids in ambient air, as in theory they should be particle bound due to their chemistry. And then a range of the different fluorotellular alcohols as well. So really interesting to see, such a unique sample, but it's just created more questions really. And then another case study that we've done internally is looking at then testing materials. So like with the pig pen, if we've been able to get some of the materials maybe surrounding the site, we could have brought them back to the lab and we could have done an analysis to see what our point source is. And the way that materials are commonly tested for emissions is through the use of chambers. And microchambers have been used for the last 12 to 15 years as a way of screening materials and understanding the emission profiles before you then do larger chamber tests to qualify what those emissions are more rigorously. And the workflow for using the microchamber is really simple. So you load your material, you set your conditions in terms of flow rate through the chamber and heat, collect the volatiles onto your sorbent tube. So we can use the same PFAS sorbent tubes as we've used in the ambient air here. And then you analyze your sample on your TD100. For this testing of materials, we used a flow rate of 50 ml/minute. A sampling time of 1 hour to try and maximize the sample that we were getting. Typically, you might take a sample for 10 to 20 minutes, depending on what you're trying to do. And this gave us a total volume of 3 litres. We also looked at whether varying the temperature increased the emission rate for the compounds we were targeting here. And the sample we chose to do this with was a waterproof child's coat. Waterproofing has long been known to be a source, to use PFAS, so it seemed like a really sensible material to pick if we wanted to get a hit. And we weren't disappointed. We've used less than a gram of coat for our testing, but you can clearly see we've got high response here for the fluorotellular alcohol, the 8,2, which is labeled FOET here, and also the 10,2, FDET, labeled here. And what we can then do with this result is, okay, so we know how much of a compound was released per gram of coat we tested. Okay, so that gives us, a number. But what we can then do is look at the emission rate. So we could say if this coat was left out in the air and it was 21 degrees C, then you could potentially see an emission rate of 0.08 nanograms per gram of material per minute. And this is what you can then use to calculate sort of exposure, and from a toxicological point of view, you can then begin to understand whether this material is going to be dangerous, knowing what we know about the toxicology of the chemicals you're looking at. So yeah, lots of different things that we can do to try and understand more about PFAS in the environment and where it's coming from. So if we then move on to our second class of compounds, our products of incomplete destruction. So completely different method now. We're looking at a TO15 type method using canisters. For this testing, we've chosen 6-litre canisters. We've got a focusing trap, which is optimized for ultra volatile compounds. So that's marked as greenhouse gases focusing trap is the one we've tried here. And then we're using the Unity CI Advantage XR, which is the canister system and the pre-concentrator. Internal standard for this, we've used a TO14A mix because it's aromatic and fluorinated, so it's quite a good internal standard to use. And for GC, we've got the 8890, a gas pro column, and then the MS is a 5977C. So the most important thing to think about when we're trying to modify the TO15 method here is our most volatile compound. And the most volatile compound, as I discussed really briefly earlier, is going to be this Freon 14. And it's not only ultra volatile, it's really very difficult to destroy thermally. You need temperatures in excess of 1445 degrees C to completely break down the Freon 14. And when we're trying to break down PFAS thermally, we're trying to break it down into water, CO2, and hydrogen fluoride. Each of those can be fairly routinely dealt with and seen as much less of a threat to the environment than all of these different breakdown products from when we're disposing. CF4 is a really potent greenhouse gas. It's over 50,000 times more potent in terms of its warming potential than CO2. So really very important we don't release a load into the atmosphere. But as I said earlier, it's also really difficult to monitor. It's literally the most volatile compound that you will see monitored with any pre-concentrator system. But it is being monitored, and it's being monitored in terms of ozone depleting lists. It's released from aluminium smelting, it's released from semiconductors, so certainly there's already systems out there which are doing this analysis. We're just applying it to a different scenario here by monitoring PFAS destruction. And the reason that we're talking about this so much now is because this will actually be the first regulated method, or rather test method, which is used for regulation for PFAS in air in the US. And that method will be called OTM 50. It's the follow-on method from OTM 45. And it's going to be used to ensure complete destruction of PFAS. So the US EPA is working on the method at the moment. They're expecting, I believe, to release either at the end of this year or more likely now, probably next year. It has identified 30 compounds for monitoring, but will also ask for basically any other compounds that are seen to be reported as well. The most important compounds for indicating destruction will be the CF4 and the C2F6. Now, because CF4 is incredibly volatile, you can only really take quite small volumes of it. And the way that the EPA is going to get around this is they're going to have the OTM 50 method will have two analysis of part of it. It will have a really low volume sample for the CF4 quantitation, And then it will have a larger volume for everything else in that mix. And CF4, typically, you're talking retention volumes of 5 to 20 mil on a typical system. So really, really small volumes. But what's also true is that if you've got incomplete destruction and you are making CF4, you will see quite a lot of it. So that small volume is not really a concern in terms of sensitivity. And because of that, this is going to be a detection by single quad, MS. Single quad, not only because it's not necessarily going to be low concentration, but also because, I mean, triple quads don't work very well for small molecules, and CF4 is a small molecule. So here's an example of a fairly clean stack sample, but it's one that this is destruction of AFFF phone. And we're really looking for the compounds right down that light end where the purple circle is for that CF4 and C2F6. Now, one of the challenges, because this is going to be a stack sample, is that you're going to have high concentrations of lots of other stuff, and you're going to have a high water content. But apart from that, you're also going to have very high CO2 levels. So what's going to be really key for this method is probably going to be matrix matched standards, because if you've got your standard which you're calibrating with made up in air that you buy in a cylinder, quite often the CO2 is actually taken out. So you're not even going to have the same amount of CO2 as you would see in ambient air at that point. And the expected concentrations of CO2 in this type of sample could be, 5% or more in the final sample. So that's a really big difference, and it's going to be a really interesting analytical challenge to see how the US EPA deals with this. We've been consulting with them on it on and off. We've been looking at doing some research on our own, actually because of work that was going on in China for a similar problem, and it's a tricky thing to solve. But do watch this space. I'm sure we'll find a solution to it soon. Okay. But if we're thinking about sort of what's possible in system performance for these compounds, stack gas sampling for them may be the beginning, but we might also want to then begin looking at these compounds more broadly in ambient air. And to do that, you're then going to need sensitivity and larger sample volumes as well to reach that sensitivity. We've taken a typical sort of ozone depleting substances list, which is made up of fluorinated compounds, CFCs, HCFCs, and others as well. And then we've looked at performance when we're taking an 800 ml sample with 50% relative humidity, so more in line with what you're seeing in ambient air. The sample you can see here is at 0.8 ppt, and you can see we've got really good sharp peaks, really great detection limits, sub ppt for all of these compounds, and great linearity and repeatability as well. So in terms of applying the CA advantage to this OTM50, we're really confident that it's going to perform really well. But we also are confident that if that OTM50 method is then expanded to ambient air, we're still in a great place to tackle that slightly less challenging matrix as well. So all of the stuff which is useful within methods like TO17 and TO15 can be applied to PFAS. We're looking at different compounds. We're looking at different method detection limits for these compounds potentially, but the versatility and the adaptability of the Marks TD instruments means that with a simple change of a focusing trap or some sorbent tube, you can take a system which has been optimized for something completely different and turn it to be able to address this new and evolving problem. Marks instruments also come with a range of other benefits, such as being standard method compliant already. We do no flow leak checks to ensure that you really high pressure or low pressure leaks in the system. We've got water management as standard. We've got internal standard addition, and we're also have eco-friendly options, or I mean, in the relation to the H2 carrier gas, potentially necessary options with the lack of helium availability now. But you can get H2 carrier gas systems. We don't use any solvents and we're not using any cryogen. So in terms of lab sustainability going forwards, you're also fully prepared for that. Ooh, wrong way. So thank you very much for your time today. If you do have any questions, then of course feel free to contact Marks. And of course you contact Quantum as well. If you have any questions, I'd love to answer them now.
Fantastic. Thank you so much, Hannah. We definitely have a few questions here, but if you have a question for Hannah on anything that we've talked about today or related, please type them into the questions section you see in the GoToWebinar control panel. All right, let's dive in here. The first one is, what are the recommended GC columns for PFAS analysis?
Yeah, so depending on what compound set you're looking at, we've got two different recommendations. So for your sort of more classical PFAS, our recommendation is a 200 ms column. It's proven really good for the separation of the acids. And then for your products of incomplete destruction, a gas pro is really your go-to for that, 60 meter preferably.
Fantastic. The next one I have here is, can this be used to concentrate PFAS in water or organic solvents like isopropyl alcohol?
So we typically wouldn't use thermal desorption for that, but Marks do manufacture a product called Sentry, which is available through Quantum, and that can be used for liquids, and it has the same trapping capability within it, so that can be used to do some more stuff with water and also solvents.
Fantastic. The next one I have here is, you discussed the instrument background being PFAS free, but what about the samplers?
Yes, so that's a really good question. Really good question. Anyone who's familiar with some of the LC methods, OTM 45 being a really good example, actually, the stack gas method for PFAS emissions. Within that, they use sorbents. What everyone has seen with sorbents is that batch to batch variation means that sometimes you have a really low PFAS background in your sorbents, and sometimes you don't. We've personally done some testing in-house to try and look at the PFAS background in the sorbents which are used for TD. What we found is that you do see some low picogram amounts from the sorbent tubes, but until we understand what the regulations are going to require, there's absolutely no way we can tell whether those are significant or not. But what I will say is that all of the data that we have produced on the triple quad uses that EPA method for determining the method detection, takes the background into account. So where we've seen background from sorbent tubes, any method detection limit we give as part of that work will include that background in it. And it was still, the method detection limits we got were still well within what you'd expect to see in ambient air at sort of background sites, so not even urban sites, at backgrounds. So for now, I'm fairly confident that even with some background from the sorbents, this method is still going to be more than capable of meeting the requirements of future regulation. But we saw what happened with water, so we'll watch this space.
We have a question here on sorbent tubes. Do you need specific sorbent tubes for monitoring PFAS, or what sorbent tube is being used here?
Okay, yep. So we've optimized our PFAS tubes to be able to take a really large volume. And that is likely to be important for ambient air. So if you to do your own PFAS, make your own PFAS tubes, you can absolutely do it. But I mean, we've already done the hard work for you. So if you're interested in buying PFAS tubes to try out, Quantum are absolutely the people to talk to, and they'll be able to guide you to those already validated sorbent tubes.
Fantastic. Next question here is, how easy is it in practice to adapt the TO17 to monitor PFAS in air?
Yeah, that's a good question, and certainly that TO17 method is what's being adapted for sort of development of tube methods for various different regulations to come. But in terms of actually setting up the analytical method, it was actually surprisingly easy. Where we found more difficulty actually was just with transferring that onto just getting the sorbents right, really. It takes a few goes to figure out how you're going to take 500 litres onto a tube, not to mention a very long time to test it. But creation of the actual analytical method is still fairly close to TO17, and we've also already done the work for you. So if you look at any of our PFAS application notes, that method would be a great starting place for anyone who is looking to adapt and try out PFAS on sorbent tubes as well.
And I've got here, when will PFAS in air be monitored more widely?
Very much up to the US government at the moment, but when OTM 50 is released, that's when we expect monitoring of PFAS in air to begin more widely. There is a stop on the Department of Defense disposing of any of their stocks of AFFF at the moment until that method comes through. So once that happens, we expect destruction of PFAS containing substances to start in earnest again, and at that point monitoring will be required. So maybe as early as next year.
We'll have to create our Google alert for OTM 50 to figure out when that's coming out.
Yeah.
And I apologize to all the smart people on here that I'm going to probably butcher this word, but I'm going to go for it, Hannah. When is the ASTM method for fluorotelomere alcohols coming out?
Like a prolon, like a pro.
Thank you.
The ASTM method for fluorotelomere alcohols, there's a bit of discussion within ASTM at the moment. We are deciding whether we run the interlaboratory study for the method before we release the method or afterwards. So it could be, end of next year is that we see a method for fluorotelomere alcohols. It could be after an interlab study has happened. So watch this space, but if you are interested in taking part in the interlab study for fluorotelomere alcohols, by GC triple quad, then please do get in contact. We are talking to labs about it now, and we've got a list of people who are interested, but always good to have more labs getting involved in this type of thing. It's a big help.
Fantastic. That's a great idea. All right. Well, we are at the top of the hour here, so I think I'm going to close us out. And Hannah, thank you so much. Thanks to you and Marks for giving us your time and presenting today's webinar. Everyone who is registered for today's event is going to get a link to the recording once it's available, which happens fairly shortly. That is it for us. Thank you, everyone. Have a great rest of your day, and we look forward to helping you with your instrumentation needs. Thanks, everybody.